Hello, and welcome to the review for the final exam for Math 201 Statistics. And there's going to be several short videos going over some of these problems. Just want to remind you that this exam review is not considered exhaustive, but hit some big highlights. So I am trying to have problems that will represent types of questions that you might be asked on the final exam, but it will not be every little thing, and they're not going to be exact problems or worded similarly necessarily, and they will be in Canvas. So a lot of them will be fill in the blanks or multiple choice. There will be some uploads as well. So it says a recent Gallup poll found that Americans plan to spend an average of $800 on gifts this holiday season. The standard deviation was 150. Assume the data was normally distributed. Construct a normal distribution with the parameters in parentheses labeled. And that should be parameters and percentages labeled. Okay, so there is my normal curve. And remember that the parameters and percentages are also the probabilities of these values occurring. And so our center is always at the mean, which would be $800. And then within one standard deviation to the left and one standard deviation to the right will be 34% on either side. So understanding that. So it's 34% likely the probability of being one standard deviation below 800, which would be $650 spent on holiday season, would be about 34%. And the likelihood of spending $950 is about 34%. And so drawing this normal curve helps us look at these standard deviation marks and their probabilities using the empirical rule. However, we use inverse, the normal distribution in Desmos to help us find probabilities and outcomes that are not on these specific standard deviations. So this would be 2 standard deviations, which is 500, and then 3 standard deviations, which would be 150. And this is 13.5%. This is 2.35%, and this is 0.15%. And you can't see my percentage symbols here. And then this would be 150, so that would be 1,100, and then this would be 1,250. So it says, what is the probability that a person plans on spending over $1,100 on their holiday spending? So that would be 2.35 plus 0.15%, which would be 2.5%. Or you might write that as 0.025. What is the Z-score of a person who spends $1,400 on presents this holiday season? Would this be unusual? So $1,400, a Z-score is taking the observation and subtracting the mean and dividing by the standard deviation. So we're looking for the average number of standard deviations. They are above or below the mean. So $1,400 subtracting 800, the mean, over 150 would be 600 divided by, not $1.50, 150. 150 would be 4. And yes, very unusual. And the reason is they are past 2 standard deviation above the mean. It says, what proportion of people will spend between $650 and $1,100? The $650 and $1,100 would be right here to right here. So these percentages in between. So that would be 34 plus 34 plus 13.5. So that would be 68 plus 13.5. So that would be about 81.5% of people plan to spend between $650 and $1,100 in holiday spending. Okay, question number 2 says, shortly after the World Trade Center towers were destroyed by terrorists, America Online ran a poll of its internet subscribers and asked this question: should the World Trade Center towers be rebuilt? Among the over 1 million responses, 768,731 answered yes. 286,756 answered no, and 248,753 said that it was too soon to decide. Given that this sample is extremely large, can the responses be considered to be representative of the population of the U.S.? And we would have to say no, because for one, we don't know where they got their data exactly. It was internet subscribers, which means that only people that would pay to use the internet or have access to the internet, only people that go to this America Online on the internet. So they really didn't take a random sample. Okay. Question number 3 says, decide if the following are valid probability distributions, and if not, write what the problem is. So the first criteria is they have to sum, the individual probabilities have to sum to make 1. And the second is that the individual probabilities are greater than or equal to 0 or less than or equal to 1. And so these are each positive, greater than 0, less than 1, and they add to make 1. So yes, that is a valid probability distribution. So the second one, we have 0.2, 0.2, 0.2 is 0.6, 0.3 is 0.9, 0.1 is 1, and they're all above 0, but less than 1. So that is also 1. And then here we have 1/8, 3/8, 2/3. So we'd have to get a common denominator here of 24. So 24 would give us, this would be 16 24s plus 3 24s plus 9 24s. And so that would be 26 24s, which is bigger than 1. So this is a no. Okay. Let's look at question number 4. It says, let X be the number of M&Ms in a 1.69 ounce bag. The probability distribution of X is shown below. Complete the probability distribution above. So because of the rules that we stated up above, the probabilities have to equal 1. We know that whatever this missing space is has to complete to make 1. So right now we have 0.45 and 0.35 is 0.8. So this must be 0.2. Okay. Find the probability of getting more than 54 M&Ms in the bag. So more than 54 means that it's everything except for 49. So that would have to be 1 minus 0.05, which would be 0.95. More than is greater than. Find the probability of getting 54 or 56 M&Ms. So 54 is 0.2 plus 56 is 0.35, and that adds to be 0.55. Find the mean of the distribution, find the standard deviation of the distribution, interpret the mean and standard deviation in the context. Okay, so to do that, we're going to go to Desmos, and we're going to create a table. Because our outcomes go in the X, and our probabilities go in the Y. And to find the mean, we're going to take the total of X star Y and divide by the total of Y. So it's essentially a weighted mean. So the average is 55.25. And then our standard deviation is going to be the square root of each observation. So actually, so let's create a new row here. And it's going to be X1 is going to subtract this 55.25. So really we can just do in parentheses here, we can say X1 subtracting parentheses, this whole formula. But we want to square, so I'm going to say shift and I'm going to square that. And then we want to divide by, no, I'm shifting, maybe a 2. I'm going to divide that whole thing by the total of Y1. Okay. And let's see here. Okay, I had to total those differences. So I've got them right here. And I had to total the square of those differences. And so my standard deviation should be 5.25. I apologize. Here is the correct formula for the standard deviation. I'm going to just put this as a note. We did it in lesson 4.2, I believe, as well. But I wanted to just throw it out there so that you have it. And I will put this link in the review as well. So standard deviation is 1.757 candies. So let's go ahead and just write that up. And so it says, on average, we expect 55.25 candies, give or take 1.76 candies in a 1.69 ounce bag. Make sure that you're noting that, because a different size bag, you're going to expect different number of candies. So catch me back for more of the review.